All right, we have a vat containing cherry cola. It initially contains a mixture of 450 gallons of cola and 50 gallons of cherry syrup. So when they use the word cola, they mean the unflavored fizzy water, and then the syrup is what gives it the flavor. So there's 450 gallons of plain fizzy water plus 50 gallons of cherry syrup. So that's a total of 500 gallons of cherry cola. And then cola, being just the fizzy water, is added to the vat at the rate of 7 gallons per minute, and cherry syrup is added at the rate of 3 gallons per minute. At the same time, cherry cola is withdrawn at the rate of 10 gallons per minute. Assuming that the cola and syrup are well mixed, write an initial value problem that describes the amount of syrup in the tank. So they're asking us to describe the amount of syrup in the tank. Amount of syrup. So we're going to let that be our dependent variable. S is the amount of syrup at time t. So what I'm trying to do is write a differential equation, because I've been given a lot of information for how the amount of syrup is changing. So I'm going to write an equation for ds dt. The rate at which the amount of cherry syrup in the vat is changing. So I'm going to have rate in, how fast it's going into the vat, minus the rate out, how fast it's leaving the vat. So they told us that cherry syrup is being added to the tank at a rate of 3 gallons per minute. So that's 3 gallons per minute in. And then it's leaving cherry cola, that's a mix of syrup and fizzy water, is leaving at 10 gallons per minute. So we have 10 gallons per minute leaving, but that's not pure cherry syrup. That's a cherry cola mixture. So I need to know, of this 10 gallons per minute that's leaving, what fraction of it is pure cherry syrup. So I need to know how much cherry syrup is in there at any given moment, that we measure by the letter S, out of 500 total gallons in the tank. Some of it is pure syrup. That's S, the amount of pure syrup at time t, 5 out of 500 total in the mixture in the vat. So that leads me to my differential equation. ds dt is 3 minus S over 50. I just reduced this fraction here, 10s over 500 to s over 50. So that's my differential equation, and then my initial condition is S of 0. That's how much syrup, how much cherry syrup is in the vat at time 0, which they told us was 50 gallons. So this is your initial value problem. A differential equation with an initial condition. All right, so to sketch the phase line, that's a line where I put on the equilibrium solutions and then arrows in between and above and below each equilibrium solution. So first I have to find equilibrium solutions by setting the differential equation equal to 0 and solving. Because when the derivative is 0, the solution is constant and the amount of cherry syrup in the vat would be a constant amount. So I solve this and I get S equals 150. So my phase line has an equilibrium point at 150 gallons of syrup. And then according to my differential equation, this equation, if there's less than 150 gallons in the tank, like say there were 0, then if I put a 0 in for S, then I have 3 minus 0, which is 3, which is positive. So I put an up arrow because the slope is going up there. Slope is positive. And then if I put in a number larger than 150, like 200, I would have 200 over 50 here, which is 4. and 3 minus 4 is -1. So my slope is negative if S is bigger than 150, which means that S is decreasing. So I put a down arrow. So this is my phase line. How much syrup will be in the tank over the long term? That's 150 gallons, because no matter what my initial condition is, my solution is going to approach 150 gallons, according to the phase line. All right, how much syrup will be in the tank after 10 minutes? So I have to solve the entire initial value problem, get a function S of t, and plug in 10. So I have ds dt equals, I'm going to common denominator to make this separable. So 3 times 50 is 150 minus S over 100, over 50. Oh, whoop. Okay, I have 150 minus S over 50. That's equivalent to 3 minus S over 50. Okay, so to make this separable, I need everything with an S in it on the left, anything with a T in it on the right. So I'm going to have 1 over 150 minus S ds equals 1 over 50 dt. And then I'm going to integrate both sides. All right, so the integral of 1 over 150 minus S is going to be the ln of 150 minus S, but then because of the chain rule, if I were taking the derivative of the ln of 150 minus S, it would be 1 over 150 minus S times -1 because of the chain rule, so I need to put a negative out there to counteract that. And then this becomes 0.02 t plus c. So I changed 1 over 50 to 0.02. All right, now I'm going to multiply both sides by -1 to get rid of the negative on the left here. So I have the ln of 150 minus S equals -0.02 t. And I'm still going to call this plus c. It's minus c, but it's an arbitrary constant, so I can do whatever I want. All right, I'm going to raise e to both sides. So e to the ln of some stuff gives me the stuff. 150 minus S equals e to the -0.02 t plus c. This is 150 minus S equals, my little trick with the e to the c becomes a new constant k. And I just have to finish solving for S. So I'm going to get the S by itself here. So I've got S equals 150 minus k e to -0.02 t. And then S of 0 is 150 minus k, which I know is 50 from my initial condition that I wrote earlier, which means that k is 100. So my final solution here is S of t is 150 minus 100 e to the -0.02 t. I have a solution. To answer the question about 10 minutes, I have to plug 10 minutes into my function. So this is S of 10. I put in a 10 for t, and I get approximately 68.13 gallons of syrup.